the podium now is open to question first from the panelists, and then we go to the group.
Very nice, really beautiful research.
Robert Schwartz, you are in the dark. Lighten up the day. All right.
Couple questions. The first one is about the enhancer that you're characterizing. Have you looked at the sequences in detail cross evolution, and can you pick out specific regulatory binding sites? That's the first question.
Sure.
And
sorry.
And if you make transgenic mice with it, is it specific to the heart and to the atria versus any other organs?
Mm-hmm. So let me answer the first question. By the way, it's great to see you, Bob, and it's wonderful, actually.
Yeah, I haven't seen you in a long time. It's nice to see you again.
Yes, indeed. So in terms of the sequence, that's the first thing we try very hard to actually dissect within the enhancer sequence. What could be the molecular signature allow us to identify the upstream transferrin factors? There are several appears to be the common ones that we may observe, including MEF2, including MILD even, and the MEF2 perhaps is one of the top candidates for us at this time. And in addition, we were also found several other potential transferrin factors that actually can contribute. So far, the sequence that we used in vivo is about, I think it's about almost 100 base pairs. So it's still too big for us to really definitively know which transcription factors are responsible. But in vitro, we actually narrowed down to much smaller, and we're in the process of identifying potential sort of top candidates at this time. For the second question is whether the reported construct in vivo are highly specific only in the muscle, in terms of tissue specific. Is that a question, right?
Mm-hmm.
Yeah. So we look into almost all the tissues, and we observed only in the cardiac and the skeletal muscle, which are the endogenous RBFOX1 expression profile, other than brain. We didn't see anything in the brain because we use this as a cardiac specific or straight muscle specific enhancer. We did not see the atria at the beginning, but after 2 weeks later, atria actually showed up. So whether it's because the atria maturation is slightly slower than the ventricle in that regards, or they undergo kind of a different transfusion factor targets, we don't know yet.
And I have a third question. When you knock out RBFOX1, and that's a really exciting discovery on your part, do you see activation or upregulation of other splicing factors that are not cardiac specific?
That's actually a really, really good question. So in the RBFOX family, there's RBFOX1 and RBFOX2. So we pay attention on the RBFOX2, which is a very close homologue of RBFOX1. It has similar binding motifs and similar RNA splicing activities, although RBFOX2 appears to have more than just the RNA splicer. They're also in the nuclei for other transcription regulatory roles. So when we knocked out RBFOX1, and we do see the slight change of the RBFOX2 expression. So it appears like it's trying to compensate a little bit. But we didn't, honestly, we didn't observe or didn't pay attention perhaps to all the other splicing factors, as you mentioned, but something we probably should pay a more closer look.
Very good.
Thank you. Questions, if not from panelists, Dr. Tagmeyer, Professor Dr. Tagmeyer.
This is mind-boggling as always. You mentioned a bit peripherally metabolism a few times, and I have simple question. You think that RBFOX1 is somehow nutrient sensitive? And the reason why I'm asking this, there's recently been a lot of attention on a time-restricted feeding and ketone body metabolism, and the really actually metabolic regulation or nutrient sensing in cardiac maturation. Do you have any thoughts on this? Because I know you have a soft spot for metabolism somewhere in your heart.
Thank you, Harry. Thank you so much.
If I knew I had another 10 years, I would apply for one of the positions that you had advertised. And
thank you so much. Yeah, that's so kind of you. And we share the same soft spots in the hearts about the metabolism for sure. And indeed, we're very interested in looking at many of the the preclinical procedures where they promote cardiomyocyte maturation through metabolic methylation, for instance. And we're looking for whether any of that also contribute to the RBFOX1 expression. And the straight answer is we don't know. We know so little about RBFOX1 regulation. We know a little bit more about the downstream. Actually, we know very, very little about upstream. And so your question is really valid and something we're eager to dive into. We do see during the transcription regulation as well as metabolic change, there's a dramatic change of many of the metabolic related genes as well as pathways. So I totally agree with you that the metabolism is very important. Yeah, thank you.
All right, we have.
Yeah.
All right, Dr. Tagmeyer. Professor Gerha, who is my colleague here, recovering from cold, he asked the questions whether RBFOX1 regulate gene expression independent of its splicing function, and what is the role of RBFOX2 in cardiac myocyte maturation? Are these two redundant?
Those are a great questions, and I have a suspicion that you are one of the very tough reviewers. We had a hard time to address that as well, but RBFOX2 expression is very different from RBFOX1. It's more, it's broad, it's more than just in the cardiomyocytes. And also during this maturation process or developmental process, its expression is high. Actually, it's reduced during the maturation, in a postnatal maturation period. So when we knock out the RBFOX1, we actually do see the RBFOX2 expression a little bit higher. We suspected that is the compensation. Your question about the molecular level, whether they can be totally redundant, the straight answer is not. We know that RBFOX1 and 2, even though they share the RNA splicing properties, and they do have a very different molecular outcome if you knock out each one or you knock out both. And on top of that, whether the RBFOX1 has function beyond RNA splicing, we certainly agree, and because there's cytosolic isoform of RBFOX1 as well, and also their RBFOX1 in the nuclei may have splicing independent properties just like RBFOX2, which has been demonstrated, but we have not really dived into that level of complexity at this time. I think that's actually what Chen Gao in University of Cincinnati, she's continuing on this line of inquiries. Thank you.
Excellent, thank you. So let's see, we have just a couple. Oh,
I saw David actually asking. Yes.
David.
Okay, great. So yeah, I'm going to ask a 30,000-foot, almost philosophical question, because we keep seeing that the things that are going on in the embryo that then have to transition after birth are more or less recapitulated, and things seem to want to go back to that kind of a state when the adult heart is stressed. But the conditions for the adult heart never really change. I mean, it's hemodynamically loaded. The embryo is not. it has to consume much more oxygen and ATP. The neonate did not have to, I mean, the embryo didn't have to do that. So in the end, is this a just really bad idea that somehow nature has encoded in our genes and want to go back to some early period, but it clearly seems counterproductive in so many ways? We don't, the heart doesn't start regenerating. We know that much. If it did, maybe that'd be useful. And is this actually found in other organs? Do other stressed organs, including, I don't know, the brain, where RBFOX1 is expressed, do they do the same thing when they're stressed? Do they try to become a fetal brain?
That's
we know about
actually, yeah. So actually, that is so interesting. We actually indeed saw the reports that RBFOX1 expression associated with the neuron maturation, and indeed in the neurological defects, RBFOX1 expression also downregulated. However, we don't know what is the consequence contributing to that, and we have the enhancer sequence in our hands. We're very eager to find out whether the same enhancer also responsible for the downregulation of RBFOX1 during stress, right? So then you will see that the same sort of a genetic imprinting actually contribute to both normal expression but also disease loss. I don't know. I think that you're asked this philosophical question, but it's actually, we ask a lot about a true implication in terms of cardiac regeneration therapy, and are we really treating the heart to promote its, preserve its function, or make it more in the fetal stage yet fail? And that's actually what we see in many of the studies. You probably recall, if you promote the cell cycle hard enough, you actually fail the heart, and that's something that we actually see that. And anyway, so that's a very interesting discussion we can have for many hours.
This
Thanks.
is Heinrich.
We have two hands.
This is Heinrich.
we have,
A quick question, and that is, in addition to the idea of hypertrophy, cancer cells hypertrophy and divide, heart hypertrophies and fails, and that, I think, is the difference in hypertrophy actually, is at the beginning of both processes.
Yeah, no, that's of course a great question, and we were hoping to, if we can grow the heart and the proliferate without fail, and then we can live forever. And that.
Yeah.
Very good. We have two hands up.
Yeah, okay. And
Roger Ho and Xinliang Ma. Roger.
Yeah, I'll be very, very quick. And then you've been excellent talk as always. Yeah, really enjoy a lot. Actually, I had a similar question as David Cass already asked, philosophic. I'm not going to ask. But I just another interesting question I want to ask you is that different people are taking different approach for this regenerative medicine. That 2 days ago there was a paper published in Cell Metabolism. What they found, I feel is really fascinating, is the sphingolipid metabolism really control regeneration. Interesting things about two enzyme SPHK1, SPHK2. SPHK2 is expressed in cardiomyocyte and then promote regeneration, and SPHK1 is expressed in cardiac fibroblast cells, inhibit fibroblast cells. So it looks like it's really fascinating. Does what you need to do, does what you really want to inhibit. And then it's really, I just want to see whether like this RBFOX1, whatever, have anything to link with this sphingolipid metabolism, control that, or just they're separate? Just that's very naive question.
We don't know. I mean, I think that's really a fascinating question. And actually, Dan Kelly made a very interesting observation with the PGC1 as well, PPAR alpha expression, part of the maturation that's mostly related to lipid and glucose metabolism switch. So I think that area of studies is still continuing, and we don't know, possibly, PPAR and the PGC1 also regulate the RBFOX1 as well. We don't know yet. Thanks.
Thank you. So Roger, last question.
Yes, Ali, thank you. I hope it's not a disappointing question being the last one, Yipin. Congratulations. So Yipin, mine is about the notice that the RBFOX1 levels are increasing in maturation, which is what prompts you to think it's driving some process. I wonder whether the team has started to think about what is driving its increase. And then the other one is in the same line of hypertrophy. If maturation does involve the heart growing bigger as the fetus is growing bigger, are you saying that RBFOX1 is also controlling hypertrophy?
So it's a very interesting, Roger. Thank you so much for addressing that. Of course, we are very much interested in what drives the expression induction, right? That's why we study the upstream enhancer and try to understand what is the sort of underlying genetic network associated with the induction. And the quest is ongoing, and we're eager to work with you on that, especially epigenetic regulatory scheme. And in terms of the downstream, you mentioned there was very, to me, I think it's really a fascinating question, whether the RBFOX1 expression can drive, the downstream, especially in the muscle maturation process that. I guess in the sense that also prevent hypertrophy in the adults. And so we did expression in the adult cardiomyocytes can prevent hypertrophy, but in the neonates, we can clearly see the cell size bigger, but in the meantime suppress the so-called hypertrophy markers like BNP and NF. So they are definitely not the same at all. They are actually promoting this maturation associated with the growth rather than the pathological hypertrophy that often observed.
Thank you. In all fairness, there's one last question, forgive me. And this is from the audience. Mengying He wishes to know whether you have looked at the calcium handling regulated by RBFOX1. Thank you.
So yeah, sorry, I may actually go through the data too quick. We look at it extensively, both in the neonatal as well as iPSL, human iPSL derived cardiomyocytes. So we look at calcium, we look at calcium transients, we look at calcium handling proteins, including SERCA, phospholamban, and so forth, and they are universally expressed higher in RBFOX1 expressing cells, and they are closer to sort of adult cell features, and especially under high pacing. And even if we pace the cardiomyocytes at 2 Hertz, they can keep up to the pacing for a very long time, unlike the control cells that deteriorate very quickly. So that's a sign of, calcium cycling robustness. And so in that regards, yes, it's promoting maturation like towards the adult cardiomyocytes. Thanks.